All right, so we're going to wrap up. Chapter deals with internal flow. A lot of this chapter dealt with how to predict the pressure drop associated with frictional effects. So you have the Moody diagram, the most popular or most well-known diagram in fluid mechanics for flow inside of pipes, and that helps you calculate the major losses. So you get the friction factor as a function of the Reynolds number and the relative roughness. And then you use the friction factor to do either the head loss, let's write it head loss, would be FL over D times V squared over 2G. And then for minor losses, the head loss boils down to the simplest form would be a loss coefficient times that V squared over 2G. What is that V squared over 2G? Velocity head or dynamic head, something like that. We then can solve piping network problems. Problems can be long, problems can be tedious, and require iteration. If you haven't already done a problem, like the one I started last time in class, where it requires iteration, you need to do it. It's not, you're going to get some benefit by attending lectures and listening to whoever's teaching the class, but unless you do it, sometimes it never sinks in, right? For your learning, you have to do it. So piping networks, often they're iterative because you're maybe trying to solve for the flow rate or the speed or the velocity of the fluid in the pipe, and you don't know the friction factor. But the friction factor is a function of Reynolds number, which means you need to know the flow rate or the speed in the pipe. So it's iterative. Then we'll close out by talking some flow measurements. This is a problem that we worked out last time. And so you have a modified Bernoulli. I like to go from here to there, state 1 to state 2. You write down the whole equation, and then you would get, after a manipulation, something like rho g z1 minus z2. That's the pressure which is due to the hydrostatic pressure that drives that flow through the pipe and discharges it. If it didn't have any gravity, you wouldn't have any flow through it, right? Okay, rho g delta z. Then that goes to kicking it out with a certain kinetic energy, 1/2 rho v exit squared, plus any pressure losses. Where do we have pressure losses? Well, we have a major pressure loss due to the straight run, and then we have minor loss due to getting into the pipe. And so this would be the major pressure loss. Major is F L over D. Here we're using pressure, so we'll put 1/2 rho V squared. And then the minor pressure loss due to getting into the pipe, this entrance loss, K 1/2 rho V squared. And since you don't change the diameter of the pipe, it stays 8 centimeters. The velocity that's traveling in the pipe, same that's used for the minor loss coefficient, same for the major loss coefficient, and it's the same for what the kinetic energy is coming out the end of the pipe. So that's good. We only have one speed V. And so you can write the equation like rho g delta z is equal to 1 plus K plus FL over D times 1/2 rho V squared. Again, I'll just ask this again. What is the name for 1/2 rho V squared? Dynamic pressure. So you see, the kinetic energy is described as the dynamic pressure. The entrance loss is the loss coefficient times the dynamic pressure, and the major loss is due to the straight run is FL over D times the dynamic pressure. So the challenge is this friction factor. Usually this is a constant. You can pick it off. It's not a strong function or even given as a function of the Reynolds number, but sometimes it is, but most of the time it's just a constant. Let's say it's a 0.5 for entry into a pipe where it's not bell mouth, it's not smooth, and it's not protruding. If it was protruding, it could be 0.8. If it was bell mouth and really smooth, it could be low, 0.03, 0.0 something. All right, depends on the radius of curvature to help it get into the pipe. And so this friction factor, though, comes typically from the Moody diagram, or also it comes from a correlation or equation, which is a curve fit. Maybe the Colebrook equation, maybe the Holland equation, or another approximation. There's quite a few of them out there. The textbook has a great, I think it's JAI, the guy that did it not too long ago, but it's set up for computer implementation. It's really not set up for hand calculations. It's some equation that curve fits the Moody diagram, does it really well. Swami and Jai in 1976, they published it. So that can be found on page 370. But it's a function, that's the key point, it's a function of the Reynolds number, which is a function of the velocity. That's why it's implicit, or you iterate. So typically you guess a friction factor, solve for V, update the friction factor, iterate. All right. But for this, if it's an 8 centimeter pipe, the exit speed coming out is around 5 meters per second. You're getting a delivery of about 25 liters per second in the flow rate. The Reynolds number, it's definitely turbulent, 4.5 times 10 to the 5th. And then if you want, what you do is you compare the relative importance of these competing terms. What was this first term? Kinetic energy. What's this one? Entrance loss. What's this third term? The major loss. The major loss, frictional loss. So if you do that, what you find is that when you add these up, you get a certain overall, but then you go back and find out that this FL over D is a 6.48. This alpha is 1, okay, and then it's a half. You can add those up, and then you find out that this is 81%. Right here, 81% of the total of the sum of those three. This is 13%, and this is 6%. How do you interpret that? Well, you would say that the head, or the supplied, goes to 81% of it's lost in dissipation in friction in the straight run, 13% to have the kinetic energy coming out the end of the pipe, and 6% went to loss in the entrance. How do engineers use this type of information? Somebody comes along and says, we need to improve the system, and you need to come up with strategies to improve the system. So you're on a team of people, engineers, and they say, well, obviously to get more flow out of this system, we need to focus our attention right here, because if we make a nice smooth inlet, it'll greatly increase the flow rate. And you see, though, that, hey, that's only 6%. You could maybe reduce it, cut it in half, it would go to 3%, but that's not going to significantly improve the flow rate. You would want to attack here. That's where you would want to do. How would you do it? Well, you would increase the diameter of the pipe, something like that, because the flow rate's very sensitive to the diameter of the pipe. Rerun that problem. Pick a smaller diameter pipe, 4 centimeter diameter pipe. Well, if we were getting 25 liters per second, I cut the diameter in half, what should I get, 12 liters per second? No, it drops down to 4 liters per second. It's a significant drop or reduction. Why? Well, the velocity went down. That's understandable. But the area went down. Okay, so you have a lot lower flow rate. It's still turbulent. You can compare the FL over D, the major loss, with the kinetic energy, with the entrance coefficient, and the major loss even became more important. It's now 91%. 91% of that elevation head or elevation pressure that drives the flow is spent in pushing it against the friction in the straight run. 91%. You really wanted to get as much into that kinetic energy component, but here you only got 6%, so it used to be 13%, now it's down to 6%. So it's sensitive, isn't it? It's sensitive to the diameter. All of that makes sense? How about you have a pipe that starts with an 8 centimeter, then you have a 4 centimeter. Both of them are the same length that we had before, so the same diameters and same lengths. You would have an entrance loss for the getting into the pipe, but you're going to have a contraction loss right here as well, aren't you? And then you'd still have that discharge. But let's go ahead and write it out so we can predict the water flow rate in this new system. I'll start slowly. I'll go from point A, or point 1, to point 2. All right, so we have the pressure at 1 plus 1/2 rho V1 squared. If you want to put the alpha 1 in there, fine, but turbulent flow, it's close to 1. Plus rho G Z1 plus any pressure gain if we had a pump. The pressure at 2 plus 1/2 rho V2 squared plus rho G Z2 minus or plus any pressure losses. So we have no pump. It is atmospheric pressure at the inlet and outlet. We neglect the kinetic energy because the large tank falling is negligible. And what we write it as rho G Z1 to Z2. That's that gravitational pressure that's driving the flow. It goes to kicking it out. Now this is a little challenging because I have the velocity at the exit. I'm going to call that the velocity in the 4 centimeter pipe. Why? Because the velocity in the 8 centimeter pipe is not the same as the velocity in the 4 centimeter pipe. So I'm going to introduce V8 and V4. If you had different notation, that's fine, but V8 is for the velocity in that 8 centimeter diameter pipe, and V4. So this would be 1/2 V4 squared. So there's a change in the subscripts on that. Then what we have is our losses. Well, where do we have our losses? We'll have a pressure loss on the entrance here. We'll have a major in the 8 centimeter pipe. We'll have a pressure loss in the contraction, and it describes it as a sudden contraction. And there's a table in the textbook which would be provided for you, or the equations would be provided for you. You don't have to memorize it for the exam. But you would need to know, oh, how do I use that information to calculate that pressure loss due to the contraction? Plus the pressure major loss in the 4 centimeter pipe. Did we account for all of those frictional losses, or did I overlook one? They look okay? So now let's go ahead and expand here. The pressure loss on the entrance, would that be 1/2, the loss coefficient on the entrance times 1/2 rho velocity 8 squared? Yeah, because it's entering into an 8 centimeter diameter pipe. How about for the major in the 8 centimeter pipe? Would that be the F, L over D, all of that for the 8 centimeter pipe? The length could be different. The diameter definitely is different. The friction factor could be different. Times 1/2 rho V8 squared. Sure. How about for the contraction? We'd have a loss coefficient for the contraction. It's going to be a function of the two diameters. Oh, you're going from an 8 to a 4. If you go from an 8 to a 4, often they have cap D for the diameter coming into it, the larger diameter, and then lowercase d for the diameter going out. And when you have a reduction like 8 to 4, a change by 1/2, then that loss coefficient, just to let you know right away, is around 0.4. And this one for the entrance is about 0.5. You've got to be careful. You could spend a lot of effort and time trying to say, is that 0.41 or 0.42 or what exactly? We're going to find that it's small in the grand scheme of things. And if somebody ran it and said, no, I really think it's 0.43, the final number would not be significantly different from the other student who said, let's go with 0.4. All right. And then we have 1/2 rho V4 squared. It's the velocity that's in the smaller diameter pipe. Look at the correlation in the textbook for that. It'll always be the velocity, or typically 99.9% of the time, it's the velocity, the faster velocity, the higher speed, the smaller cross-sectional area.
May I ask where you find those 0.5 and 0.4?
Sure. It's table 8 in the textbook. I think it's number 8.2, table 8.2 or figure 8.2. Table 8.4 and table 8.4 on page 377 of the textbook. And there, again, somebody else may read it and say, no, I think it's 0.39. Oh, I think it's 0.42 or 0.41. Just get a number, you got to go, right? As long as it's reasonable. And then we have plus F L over D for the 4 centimeter pipe times 1/2 rho V4 squared. At this point, you have a choice. It's like, hold it, I got 2 speeds here. I need to convert one of the speeds, like say V8, express it in terms of V4. So we can go to continuity. If you go to continuity, does the volumetric flow rate through the 8 centimeter pipe equal to the volumetric flow rate through the 4 centimeter pipe? Is that okay? Is that a good equation? So that the velocity at the 8 is the area of 4 divided by the area of 8 times the velocity in the 4 centimeter pipe. The area in the 4 is pi d squared over 4, so it boils down to the diameter of the 4, the diameter of the 8 squared times the velocity in the 4. Why would we do that? So that we can rewrite this equation as 1 plus, I'm going to put numbers here, 0.5, well, no, better not, K entrance times, get rid of this, times D4 divided by D8 squared plus F L over D, all for the 8, times D4 over D8 squared plus K, get rid of this, contraction, plus F L over D, all for the 4. All of that multiplies the same dynamic pressure of 1/2 rho V4 squared. Did that make sense? You follow that logic? Okay, so at this point, what I'd like to do is substitute some numbers, but to get the friction factor, it's like, what friction factor do I use? Almost anything close will work. A friction factor between 0.02 and 0.04 will work, somewhere in that range. 0.03, run with it. You do 1 iteration, 2 iterations, you're going to zoom in real fast. Prove it to yourself by doing that. Okay? Just prove it to yourself by doing that. Now, I already know the answer, solved the problem already, so the velocity coming out the end, V4, the final answer is going to be around 3.3 meters per second. You don't have to be clairvoyant. You don't have to have a great guess on it. It's probably best to just get a friction factor, 0.02, and run with it. Okay? And then the velocity in the 8 is going to be a lot less, isn't it? Look at this. Won't it be 1/2 squared times the velocity in the 4? Won't it be 1/4 the velocity so the speed in the pipe, the 8 centimeter pipe, is 1/4 the speed in the 4 centimeter pipe. True? So that would be much lower. I don't remember what the number is. I have to look for it on my sheet of paper. Well, just divide it by 4, and I don't have it in front of me. Okay, I think it's 0.83. Yeah, there you go. Now, one other thing that's probably worth doing is you see this d over 4 to d over 8 squared. Well, the ratio of the d's is a half. I messed up a little bit. When I forgot to write this 2. See what that factor of 2 does? When you replace V8 in that by V4 times the ratio of diameter squared, this becomes, let's fix it right now, 4. That makes sense? So this ratio here is not a fourth, but guess what that ratio is? Large diameter pipes make it easy for fluid to go through it at relatively high speeds. And so that really knocks it down. So this is a 16th right there. All right? Okay, so what I was going to do is I was going to write out some numbers. So if you put the 1 for the kinetic energy, for the entrance on the 8 centimeter, it boils down to 0.0313, too many digits. For the straight run on the 8 centimeter, 447. For the sudden contraction, 0.4. And for the straight run of the 4 centimeter, that FL over D comes in at 15.95. All times 1/2 rho V4 squared. If you sum those up, it's 17.80 times 1/2 rho V4 squared. Now what we do is we go and we say, how important was the 1 to contribute to this whole sum of summing up to 17.80? Well, that contributes 5.6% of it. What does 0.2%? 0.2% is negligible in these type of calculations. The next one is 2.5%. The sudden contraction contributes 2%, and the straight run in the 4 is 90%. 90% of what? 90% of the 17.8. So you can interpret this as your gravitation and the elevation difference drives the flow. Where does it go? 90% is lost or dissipated in the 4 centimeter straight run. The next biggest is about 6% is the kinetic energy coming out the pipe. What's the next biggest? The straight run on the 8 centimeter, which is about 2.5%. You're really getting negligible. And about the same as the contraction in the middle, that sudden contraction at 2%. And then really negligible is the little bit of loss getting into the 8 centimeter pipe. All right, so at this point, I have to scoot down a little bit or just tell you that you already know this rho G delta Z. We have that constant. Solve for V4. Go back and iterate, get better estimates of F, the friction factors. Then do it one more time, and this will be your final answer. And then the final volumetric flow rate, which we're asked to solve for, you can calculate it using state 4. And so the volumetric flow rate is 4.15 liters per second. Yes, sir?
How do you know what you need to do iterations?
Well, you're stuck. How do I know what F is? I got to get the friction factor. And the friction factor, you're thinking, okay, I know how to get it. Give me the Reynolds number, relative roughness.
Excuse me, Dr. So how about like when we did the fraction, basically we can't estimate the Reynolds number and get velocity. why do we do third iteration or fourth iteration?
Oh, as soon as you see that it's not changing, you're done. That's how you know you converged. It's not changing. And this will converge even with a fairly poor guess very quickly. When 1 to 2 iterations, you can see that you're there. But you really should do a few by hand. You really need to do a few by hand.
Did you just pick a random F to start with?
I picked a bunch to start with. But I really did it last time. I started assuming a friction factor because on the Moody diagram, I had more confidence that friction factor is only going to be in this range. Remember that discussion? I didn't guess a velocity on the exit. I guessed a friction factor. And then I was able to get the velocity and then update the friction factor, update the velocity, update the friction factor, update the velocity. Okay? What was the volumetric flow rate when we just had the 4 centimeter only pipe? It was 4.21 liters per second with only the 4 centimeter pipe. We added the 8 centimeter pipe. Oh, it's 22 meters long. You would think that it would drastically reduce the flow rate by adding that 8 centimeter pipe. But that whole 8 centimeter pipe almost did nothing. See that? Right. Yes, sir.
After the first iteration, you correct. Try to get your second friction factor.
Oh, you have a new V. So you get you're solving for V4, right? So you have V4. Then you go and get the updated V8. Then you get the friction factor in the 4 centimeter pipe because of the Reynolds number in the 4 centimeter pipe, and the friction factor in the 8 centimeter pipe. No, it updated Reynolds number in the 8 centimeter pipe.
And you do the whole equation again.
Then you just do this equation again to get a new V4. They will jump so fast to start to converge. If you do it 3 times, you'll be amazed. It'll go right fast for this problem for sure. Okay?
So the V's have to start.
Well, the friction factors will converge. The Reynolds numbers will stop changing. The flow will stop changing. Right. Yep. Okay. Ready for a clicker question? Which case? Now, this is different. We've never analyzed this case. So please let me explain it. What we have is we have a tank with the 8 centimeter pipe, 8 centimeter pipe. This is 22 meters. Hey, we've done that before, but this has a little elbow and an elbow and then a 19 centimeter. Then a 4 centimeter pipe, a 22 meter long. But it goes into a bottom of a tank. Now, you compare it to this system where I have a 8 centimeter pipe, 4 centimeter pipe, and it's discharging at the top, just like what we analyzed. So which case will have the higher flow rate? Will case A have a higher flow rate, or case B have the higher flow rate, or case C the same? How long should I give you? Should I give you more than 30 seconds? This answer is not coming out of the book. This answer is coming out of your experience. I'm going to give you a little more time. There you go. Think about it. Look at all the numbers. Analyze it in your head. No time to really run numbers. Which one's going to give you the higher flow rate? All right, you're down to 20 seconds. Is everybody in? All right, have to call it a question sometime. All right, now look at I'm going to outline a little bit of the strategy we had. We had rho g delta z equal to some sort of one, we wanted to come out of the pipe, end of the pipe fast, plus some loss coefficients for the minor, and then the FL over D's for the majors, and then we had the dynamic pressure 1/2 rho V squared. Now, I would probably do it this V that you're solving for, the V at the 4 centimeter pipe, and they both have discharge out of a 4 centimeter pipe. One is submerged, one is not submerged, okay? But what drives this flow? Oh, these reduce the flow rate. The friction reduces the flow rate, true? But what drives the flow, makes it happen? And that elevation difference, right? So let's do this. We start here. We're going to do Bernoulli's, Bernoulli, modified Bernoulli. That's where you end. Let me ask this question. The walls of the pipe, the tank, go up here, and the fluid level goes up to here for that tank. Is there going to be any flow? No. No, there isn't going to be any flow. True? All right. So what drives the flow is 7 extra meters. Compared to this system right here. Here's Bernoulli, and it goes there from 1 to 2. And so what was the delta Z for this case? 10 meters. What was the delta Z that drives the flow in this case? 7 extra meters. Did he do it right? Is it 7 extra meters? Is it a greater delta Z? You're saying, Professor, there's going to be more losses because of more pipe, longer pipe. But look at the pipe, it's large diameter. You have more elbows. Yes, minor losses. Little problem that we just solved, they're small as a fraction or percent. That insight that you gain. So this loss coefficient here, that will be 1. A submerged exit is a loss of 1. All that kinetic energy is dissipated in the flow that it shoots out into that tank. So let's see how you did. Oh, what's the answer? Which one's going to have the highest flow rate? Why would B have it? Come on now. It's going to be A. It's going to be A. And when you take a look at the sum of all of this is roughly, if I looked at, said this is this case, down here is this case. You have rho, G, delta Z. You had 1 plus some K minors and some FL over Ds plus, then you had 1/2 rho V squared. I'm saying this is not dramatically different than that for these two cases. What's different is the change in the elevation. You have more head driving the flow in that first case, case A. All right, let's solve it. Here's the same problem, but now we have a submerged. So start Bernoulli from 1, right there, from 1 to 2. And so it'll have the rho G delta Z that drives it. The delta Z now is larger. What did we say it was? 17 meters. And you're going to have a loss for the exit. I'm going to put a 1 there. You'll have a loss for the run, straight run, in the 4 centimeter pipe. FL over D in the 4 centimeter pipe. You'll have a loss because somehow you're going to have kind of an elbow with a contraction. Okay? I'm going to say that that's some K contraction elbow in the 4 centimeter pipe. Plus, we'll have the major loss FL over D in all of the 8 centimeter pipes. But I know that then I have to multiplied by a ratio of diameters because everything's going to be linked back. So this is going to be D4 divided by D8 to the fourth power, true? Then we're going to have some K's for the elbows and the K for the entrance and the D4 over D8 to the fourth power. All of that, right, is multiplying the velocity head 1/2 rho V4 squared. I tried to, it'll take you a couple steps to get to that equation because we've done it before. Hopefully it's understandable. Yes, sir.
The major loss in
This term.
vertical pipes and the horizontal pipes, are they calculated the same or there is a small difference?
So this length right here, the length of the runs in the 8 centimeter pipe is 22 plus 19. 22 plus 19 meters.
Yeah, let's say they have the same length and the same diameter. The major loss will be the same?
The friction loss, the major friction loss, doesn't depend on if it's sloped or straight up and down or anywhere. That's right. Yeah. Now, what your intuition may be saying, well, I have water in a pipe, and maybe if it's horizontal, I have some air at the top. No, these pipes are full of water, and they're flowing at the velocity profile, which would be a turbulent profile. Nothing. I could see where somebody is like, hold it, something's got to be different. Well, when you're going down, you're losing elevation, changing elevation. Horizontal doesn't change elevation, but that's accounted for in this term over here, what drives the flow, the change in elevation. So so this length is a little bit longer. This contraction elbow, again, what we would do is I would do this. I would put it as 0.3 for the elbow and a contraction of 0.4. There's not a lot of detail. They do have these, what do they call them? Anybody ex-plumber? Street elbows, where they come in one diameter, turn 90 degrees, and go out a different diameter. They're very expensive fittings. People try to avoid them. Usually just have, inlet, outlet, and then put a reduction on it, a contraction on it. So if you did it that way, which is probably the way it would go, you would put a contraction of 0.4 here. And then on the elbows, how many elbows do we have? We have 2 elbows, 2 times K elbows. That makes more sense. Okay. And well, I'm going to say that this is 8 centimeter in, 8 centimeter out, and then immediately after it, we're going to have a reduction to 4, a sudden contraction to 4. All right, so let me kind of run through these numbers here. If you guess and iterate, and I would start by guessing the friction factor, guess it around 0.025 will be a good guess. You could find that the total sum of all these coefficients comes in at around 18.03 1/2 rho V4 squared. And then you have rho G delta Z. And the first term, 1. Then for the major friction, it's 15.93 in the 4 centimeter pipe. For the contraction, oh, I forgot also, this 1 is the K for the expansion, the submerged expansion. All right. And then we have 0.4 for the contraction. For the straight run on the large diameter pipe, it's 0.62, and then the two elbows and the entrance is 0.07. So this right here is 88.4%. And then the other losses for the 4 centimeter, I lumped them together as a 7.8%. You can bust them apart if you like. And these are small. It's at 3.5% and 0.4%. Really, if you have a large diameter pipe in the network, and then you reduce it to a small diameter pipe with the same flow rate through the pipes, well, the large diameter pipe has really small, negligible resistance, and that's what we're showing. And so we calculate that the volumetric flow rate, AV, is 5.141 liters per second. Well, what was the solution to the previous problem? Well, the solution to the previous problem was it was around 4.2. So the flow rate went up by bringing the flow down and having it go in the bottom of the tank. It's because of the elevation difference, a greater driving pressure. Yes, sir.
How come B2, shouldn't point 2 be at the exit, not at the top of the tank? Because wouldn't the velocity be 0?
This is, I have a loss coefficient K loss for a submerged, and that coefficient's 1. And so I put it right here for the submerged expansion.
No, but I mean, like, you're assuming that the B1 is 0 because it's a large tank. Wouldn't B2 also be 0?
That's right. So this V2 is 0 right there.
Isn't B4 technically B2? Or no, it's not.
I'm trying to get the speed out the pipe. Yeah.
You're just guesstimating on your 0.4 for your loss of that contraction, right?
Well, that's the same 0.4 we used before. You have to read it off that chart.
Yeah, because it would be 0.5, I guess would be the ratio. I'll just say it would be lower, but it's trivial.
Hold it. If you have a sudden expansion, 100% of that kinetic energy of the flow coming in is dissipated. And so all of it, so that loss coefficient's 1, not on the sudden contraction, but on the sudden expansion.
Yeah, on the expansion, that would be alpha, and you got 1. Yeah, I see.
Yeah, alpha's, I'm using alpha 1.
I was talking about the 0.4 for the contraction. It should be more like 0.25, but I'll just say it's trivial to read the chart.
No, you can check me on that, but I'm pretty sure it's 0.4.
Oh, wait, it's d squared over d squared, not d over d.
It's d squared over d squared. That's it, yeah. All right? All right. Throw in a pump. Once you now have it without pumps, you put in a pump. What's the pump going to do? Well, it's going to, if it's draining, it'll even help it drain faster, or it'll allow it to take it up the elevation scale. And so let me do this. Let me write the equation starting carefully. We'll start here, go through the pump, and come out, and we're going to discharge right there. Okay, now it's not a submerged discharge. It's an open discharge. We'll call this state 2. There's no difference in the diameters of the pipe. So we're just going to use V as the velocity in the pipe. It's the same diameter. But let's take a look at where we have loss coefficients. Which one is here? Entrance. What's this one? Elbow. What's this one? Elbow. What's this one? Elbow. Do I have a loss coefficient for the discharge? Not in the open, but when I have a discharge that's submerged, yes, because all that kinetic energy is dissipated. And it's a discharge coefficient K of 1 on a submerged discharge. Okay. Now, let's go ahead and write it out starting. So we have P1 plus.
Will there be no loss coefficient in the pump?
The pumps, what we have is they get more complicated. I'm going to avoid discussing pumps until more turbo machinery. A lot of times they have slightly different suction line than discharge line, larger diameter suction than smaller diameter discharge, but it's embedded in the calculation of the pump, the efficiency of the pump, things like that. All right? Right here, the mechanical efficiency of the pump is 76%. And they give us the volumetric flow rate through the system, and they want us to calculate the power needed to drive the pump. It's like the power that an electric motor supplies to the pump. That's going to be greater than what gets into the fluid, the pressure increase in the fluid. But let's write Bernoulli's. So let me go ahead and put the alpha 1, 1/2 rho V1 squared plus rho G Z1 plus any pressure gains because of pumps equal to the pressure at the end plus alpha 2, 1/2 rho V2 squared plus rho G Z2 plus all of those pressure losses. Let's go ahead and write it. The pressure loss due to the entrance, the 3 pressure losses from 3 elbows, plus the pressure loss, let's say major. I think those are the 3 we have to account for. Getting it in, 3 elbows, and the major. Did I miss one? Is it okay? Okay, now, again, this book likes these alphas. A lot of books just say it's 1, okay? What is alpha again? Kinetic energy correction factor, right? And it's around 1, so I don't like to write them in the equation myself, personally. All right, so this is the same as that pressure. They discharge the atmospheric pressure. It's a large tank. Now, what do we have is we're going to have that the pump, what it has to put in, has to lift the water. It has to lift the water. Z2 is greater than Z1, isn't it? And then it has to do let me write it in 2 lines. It has to kick the water out, 1/2 rho V2 squared, the kinetic energy of the water going out, shooting out the end of that pipe. And then it has to speed it up. Not speed it up. It has to overcome the frictional losses. What's the equation for the frictional loss on the entrance? K entrance. Then you're going to have 3 times the K of the elbows plus F L over D, all of that times 1/2 rho V squared. And that's the same V. So I'm just going to get rid of the subscripts on the V. It's the same V. Might make sense? So it's rho G delta Z plus 1 plus K entrance plus 3 K elbows plus F L over D times 1/2 rho V squared. I don't know if I can make it more readable. Hopefully that's readable to you. Yes?
So you just said that the pump has to overcome the friction at the entrance, but the pump is placed right before the entrance.
Oh, okay. Let me ask. Tell me a little bit about if I went from this point right here, call 1, point 1, and I said that this point right there in the tank. Tell me a little bit about the pressure between the 2 points. Which one has higher pressure? The first one or the second one? Higher pressure. Second one, because it's lower in the tank. But once you get close to the inlet to the pipe right here, tell me a little bit about the pressure there. You're drawing it into the pipe. And right here, right before the pump, it's very low pressure. And then there's a big pressure gain across. And then it's pushing till it's out there. So I think you were asking me a question about the pressures. I don't know if that helped, but It's flowing fluid, and the pressures are not all described by simple hydrostatics.
So to make it clear,
Okay, I'm going to have to cut it. I'm going to get too many little discussions going, okay? So let me do this. You have to solve these problems on your own. Even though I may be the best at explaining it, I'm trying to explain it. I'm trying to show you the spots where you're going to probably conceptually struggle with it when you struggle and solve those homework problems. But I just absolutely know it, and you know it too. A good teacher can only help you learn. You do all of the learning. Learning is done by the student. And so if there's any credit any teacher takes about being a good teacher, they just help the student a little bit. The student's got to put in the sweat, blood, and tears, but let's go. You see why I wrote the equation this way? The pump has to lift it, has to kick it out, has to accelerate it. It's going to draw it from a stagnant tank, and it's going to go out with kinetic energy. And it has to overcome the friction, the minors and the major losses. This is one of those where you would guess a friction factor, do a couple iterations. It'll go quickly and zone in or converge to a solution. And that's, well, actually, you don't even have to iterate. What am I talking about? They give you the flow rate right here. 340 times 10 to the minus 3 meters cubed per 60 seconds. They give you the area of pi d squared over 4. You're able to calculate the velocity is AV divided by A. It's right at 2.004 meters per second. You're able to calculate this velocity pressure right here. It's 2008 Pascal. The Reynolds number comes in for the flow in the pipe, 1.35 times 10 to the 5th, turbulent flow. You assume roughness of 0.15 millimeter for some galvanized pipe, steel pipe. You then get the relative roughness, 0.0025. Using that information and that information, you get a friction factor, 0.028. After you solve a few of these problems, they look reasonable. So this term right here is 25.67. The 3 elbows are 3 times 0.3, which is 0.9. The entrance is 0.5, the 1 right there. I like to, why did I put a parenthesis right there? I like to try to say, look at this is around 92% of the overall contribution there. This is 3.2% up due to the friction. This is 1.8%, and this is 3.5% or right around there. Okay, so what we do is we have the rho g delta z. The delta z is calculated. Can you see what the delta z is? Is it 20 meters? And so the pressure that the pump has to put out is 196,000 Pascal. If the pump can't have a pressure of at least that, it won't even be able to push it up the pipe. If it just pushes it up, if the pump only puts out 196 kilopascal, it'll just be able to fill the pipe and hold it there and not really spit it out. But it's going to have to spit it out or have a higher pressure because it has to overcome the friction, etc. When you calculate what the other component is, that's 56,425 Pascal. So the pump has to put out a total of 253,000 Pascal. Where is it going? Well, you can backtrack. I got to scoot down. I didn't want to. But 78% of the pressure that the pump puts out goes to just lifting the water. And then 22% of it goes to overcoming the friction and giving it sufficient velocity head or that kinetic energy at the exit. So once I know what the pump has to put into the system, and I know the flow rate, I know what the fluid power, what that fluid power is. It's the product of the pressure gain in the pump times that volumetric flow rate. It comes in at 1.43 kilowatts. I then use the efficiency. So the electric motor has to supply, because of the pump's efficiency, more than what gets into the fluid. And for our pump, it was 76% efficient. So the electric motor supplies 1.88 kilowatts in. All right. I didn't mean to shut you down on questions, but I want to make sure. Did anybody have a question? Yes, sir.
When you say negligible minor losses, I know it's contractions, expansions, elbows, entrances, exits.
Right.
Now, when it says negligible head loss,
Well, it's
I've seen some weird things.
okay. We use head loss, and I'll do it all the time, and pressure loss is almost interchangeable because all it is pressure loss divided by rho g, you got head loss.
Take it out of your Bernoulli equation.
Yeah. So, but the minor losses in a lot of cases are negligible. In this case, it's negligible. But sometimes you'll have a lot of fittings and contortions and reductions and expansions and not many straight runs. In those piping systems, minor losses are major. The significant.
Yeah, they add up.
They add up. Yes, sir.
Like in the previous problem, if we were to submerge the outlet onto the bottom of the tank, would that make the system more efficient?
Okay.
This one?
Okay, here's a good question. Maybe I'll turn it into a clicker question. Let's say the person stops right here and he comes in and he has a submerged outlet right there in the system, okay? Which one is going to have, for the same pump, a higher flow rate? The original system, case A, or the new system, which is cutting right here and having a submerged outlet, case B? Which one will have a higher flow rate? I will start it, and there you go. Here, answer C, they'll have the same flow rate if you would like to choose answer C. Everybody have enough time? Everybody get your answer in? All right, so what it is the pump. Will it affect this term by making that change? Well, wouldn't I take the Bernoulli and go from 1 to 2? And I don't have a graphic on here, but that's the change. True? I still would have, now I'd have a submerged loss coefficient, which is the same as throwing it out with kinetic energy at the top. So those would be the same. I'd have the same 90-degree turn. I'd have the same length going horizontal, but I would have a slightly lower length because I wouldn't have to lift it as far. So the major loss would go down a little, but where would be the biggest change? The difference in Z. Now, somebody says visually, you didn't give me that number, did you? You needed to give me a number where this came up. Well, I didn't anticipate the question, okay? But I would have probably said this is maybe 32 meters, meaning that there's a 3 meter less lift that the pump has to provide, hence greater flow rate for case B. Greater flow rate for case B.
Does the pump have to fight against the water in the top tank pushing back on the pump?
That's modeled as the kinetic energy dissipation of that submerged inlet. That is, no, it's included. But it's going to have the same effect as it being kicked out with kinetic energy at the unsubmerged outlet. Flow measurements. You already studied the pedostatic tube, true? Nobody should pass fluid mechanics and not know and be able to describe the pedostatic tube. You should know that, right? So it's covered now twice in the textbook. So with the pedostatic tube, what's key? The fluid at that tip comes to rest. So if you're measuring the static pressure in the fluid using the ports on the side, that will have the pressure at the tip will be the stagnation pressure. It'll be greater than the static pressure by the amount of the dynamic pressure. So the pressure at, let's say, 1, the tip, greater than the pressure 2, the static pressure on the sides of that pedo probe, will be equal to the dynamic pressure. You use that equation, V is equal to P1 minus P2 times 2 divided by rho, take the square root, voila. It gives you a very accurate, very easy to use, often used method for inserting a probe into a flow field and determining the velocity of that fluid in that flow field. Well, there's other type of flow meters. Here's an orifice meter. So they put that little protrusion in here to cut down the diameter. So the flow's going to go across that orifice. What do you think? The pressure here is going to be measured. The pressure here is going to be measured. There's going to be a pressure drop. Why? Minor losses because of that orifice. And what they do is they calibrate that orifice, and then they can put out curves, and other people can accurately measure fluid flow from pressure measurements. Well, what's the negative aspect of having these obstruction flow meters? You're always having a artificial pressure drop in there. And so you're always having to have some pumping power lost. Here's another one, which is a flow nozzle. It has more of a fine-tuned shape. And these shapes are very precisely defined. Typically ASME or ANSI has the shapes defined for these, and well-calibrated orifice and flow nozzle flow meters. They typically have equations that look like this. They're saying, you measure the pressure loss. Here's P1, here's P2. You measure the pressure drop. Multiply by 2, divide by rho. You know what? That looks a whole lot like the pedostatic. You have beta. Beta is a ratio of the diameters, D over D. Is that squared? Or you have to look at the equation, but I believe it's just the ratio of diameters. But then you take it to the 4th power here. That would be like the ratio of areas squared. Then you have the nominal or smallest diameter giving you the nominal area, A naught. That would be pi d squared over 4. And then some discharge coefficient, which has to be experimentally measured. But once you have that, you sometimes curve fit it as a function of Reynolds number. You have a very accurate flow meter. What would be this type of flow meter? It's an obstruction because it has a reduction in diameter, but then it's trying to have a gradual reduction and then a very gradual expansion. What's it called? Venturi. When we explained or studied Venturis, when we just did Bernoulli's equation, right? Doesn't the pressure here go down versus the pressure here? The pressure in the throat is lower in a Venturi. But then there is going to be some pressure drop in the Venturi. You're going to try and measure it because you're going to slow down the opening up. Maybe it's a 15% opening on the Venturi flow meter so that you avoid separation. True? All right. Too many flow measurement devices. This book really goes above and beyond in exposing students to positive displacement flow meters, turbine flow meters, variable area rotometers, ultrasonics, vortex flow meters, hot wire anemometers. Let me just quickly explain hot wire anemometer. You have a wire with known resistance, and you pass a current through it, and with that current through it, you will dissipate some heat and it'll get hot. But if you have fluid flow, like airflow, over it, guess what? It cools it down. And the resistance of that wire is well calibrated as a function of temperature. So you measure the voltage across for a given current, and you infer then the resistance, and then you can infer back the temperature of the wire, hence the convective cooling, hence the airflow. It's pretty complicated, isn't it? But it boils down to something they can sell you relatively inexpensive and use. It's pretty robust. Laser Doppler velocimeters and particle image velocimeters. So make sure you know the pitot tube. We just solved for an obstruction. The rest of these are more, you've been exposed to them, but it's hard to have an exam problem. Here's one of those obstruction flow meter problems. So we have water flowing through a nozzle. This is that nozzle right here, used to measure the flow rate. The inlet is 3 centimeter diameter, so cap D is 3 centimeters. The nozzle exit, lowercase d, is 1.5 centimeter diameter. The pressure drop is measured to be 3 kilopascal. Part A, determine the head loss. That's going back to your question. It's like pressure loss, head loss. We almost use them interchangeably. I know I do. So how do I go between pressure loss and head loss? Just divide by rho g, the weight density. And so we have 3 kilopascal. You have 1,000 kilogram per meter cubed, 9.81 meters per second squared. You've done those units so often, and this comes in at around 0.3 something meter. There. All right. What about the flow rate? Well, we look at our flow rate equation. The volumetric flow rate is given by that minimal area. That minimal area is pi d squared over 4. We can calculate that. The discharge coefficient. This discharge coefficient is a function of the Reynolds number. Hence, fluid mechanics is saturated with this. I don't know that, but it's part of needing to be able to calculate it. Guess and iterate, okay? And it typically converges quickly. For this problem, for that nozzle flow meter, that discharge coefficient as a function of Reynolds number is given on page 393 of the textbook. It's equal to 0.9975 minus 6.53 beta to the half divided by Reynolds number to the half. Okay? And beta is the ratio of diameters. All right, let's finish out our equation for the volumetric flow rate. You have the square root of 2 times the pressure loss divided by the density, 1 minus beta to the 4th. So we know the pressure loss, the density, we know the beta is the ratio of the diameters, we know the area, this discharge coefficient, so what you have to do is guess it, then iterate, try 500,000 or something, 10 to the 5, 10 to the 4 for that Reynolds number. get an estimate of the volumetric flow rate, then update and iterate. When you do that, you find that the volumetric flow rate comes in at 429 times 10 to the minus 3 meters cubed per second. And the velocity in the pipe is the volumetric flow rate divided by the area in the pipe. So that velocity comes in 0.607 meters per second.
How do we find CD when we iterate basically the fraction and what else is the second part, negative 6.53 beta? How did we bring that?
Well, beta is known for this problem. It's 1.5 divided by 3, so that's 1/2. Beta's done, but we don't know the Reynolds number because we don't know the volumetric flow rate and the velocity. So guess C sub D close to 1.95. Oh, what did C sub D converge to? C sub D converges to about 0.9 something. 0.96. Okay. All right. Song, glad you're here. This is the problem you asked me about. Remember? So let's solve this problem. This is inspired by a question in office hour by Song. So let's take a look at it. The pressure drop for laminar flow in a pipe. Notice that I added this word laminar flow in the pipe, okay? Or laminar pipe flow. Is determined to be 100 kilopascal. For the same flow rate, if we reduce the diameter of the pipe by half and the flow remains laminar, the pressure drop will be, and then it's multiple choice. Is it 25? Is it 50? Is it 200? What is the pressure drop? The pressure drop is 100 originally. So let's break it out like this. Here's my original. Here's my new system. Let's call the original case 1 and the new system case 2 for subscripts. And we have that the pressure loss for case 1 is 100 kilopascal. And we want to find the pressure loss for case 2. That's what we're looking to find and select it from A, B, C, D, or E. The flow is laminar, but what you do is you have the diameter of the pipe given, but the new diameter of the pipe is 1/2 the original diameter. True? We have AV is 1 and AV of 2. So what is the volumetric flow rate? It's the same volumetric flow rate. True? So try to organize the information as you're going down. Now, if you have the same volumetric flow rate, talk a little bit about the area 1 and the area 2. Well, the area 1 is pi d1 squared over 4. True? Isn't this going to be pi d2 squared over 4? But I could substitute for that d2 is 1/2 d1. I know I'm being a little pedantic here, but being clear to help guide you along the process so that we find we have 1/2 squared times A1. A new area, you cut the diameter in half, but the new area is 1/4 the old area. True or false? Okay. Now, what about the definition of the Reynolds number? What is the Reynolds number originally? Rho V D over mu. Now, rho is not changing, mu is not changing, but is V changing? Well, if it is, I better put V1 and D1 there for velocity case 1 and diameter case 1. And then I'll come over and I'll say, for the second case, isn't the Reynolds number rho V2 D2 divided by mu? Sure. So let's leave the rho and the mu alone, but let's replace V2 by what? Well, I need to work that out. I should have worked it out right now. If you come to this equation right here, V2 and A2 are equal to A1, V1. Hence, V2 is equal to V1 times A1 over A2. And we just worked out what A2 and A1 are. The ratio is, it's equal to 4V1. Pause, you think about it. For the new case, I went smaller diameter, and now the flow is 4 times faster. Is that correct? Is V2, the new flow speed, 4 times faster than V1? Good. So what we do for V2, we put in 4V1 there. And then for D2, what do we put in? 1/2 D1. So that we have the rho V1 D1 divided by mu, but we have it multiplied by 4 over 2, which is 2. So for the new case, the Reynolds number doesn't go up by 4, it just doubles. It's the factor. Okay, see how that Reynolds number changes? Now, because it's friction factor, because it's laminar flow, is that 64 over the Reynolds number? Well, friction factor for the new case is 64 over the Reynolds number for the new case. The Reynolds number of the new case is 2 times the Reynolds number of the original case. So the new friction factor is 1/2 the original friction factor. We're almost ready to put these pieces of the puzzle together, because the pressure loss for the first case, I know it's given numerically, but it's equal to the friction factor, the length, the diameter, 1/2 rho V1 squared. True? Let's go ahead and write it out over here. Pressure loss for the second case. Friction factor, the second case. Length over diameter, the second case. 1/2 rho V2 squared. What do you replace for friction factor of 2? 1/2 friction factor 1. Length, there's no change in length, true? But diameter 2 is equal to 1/2 diameter 1. True? And then we have 1/2 rho V2. Well, V2 is 4 V1 squared. I tried to fit it on a page, but I'm going to have to scroll down. Sorry. So the halves go, and what we're left with is 4 squared times F1 L over D1 times 1/2 rho V1 squared, which is 16 times pressure loss 1. So the original pressure loss 1, I can scroll back up, right? So it's going to be 16 times 100 kilopascal. So it comes in at a whopping 1,600. All right? Why did I put, yeah, that's a typo. Take away that kilo. Yeah. Thank you. Anybody else? Well, we're done with the internal flow.